What is it that hides behind the silence of the universe, waiting in the darkness where our questions burn brighter than the stars themselves? The cosmos stretches before us like an endless ocean. Its surface glitters with suns, yet beneath that surface lie depths we cannot measure. Galaxies drift and collide, shaping islands of light in a sea without shore. Black holes consume matter and time, swallowing even the very light that dares to approach. In this vast expanse, our understanding flickers like a fragile candle against a storm. Science has carried us far. We have mapped the spiral arms of galaxies and traced the afterglow of the Big Bang itself. We have split the atom and watched particles dance in collisions at the edge of light speed. Yet the deeper we look, the more the universe resists our certainty. The laws we thought unbreakable bend into riddles. Equations that promised order dissolve into paradox. Some mysteries are written in the faintest ripples of ancient light, drifting across space for billions of years. Others are hidden inside the smallest particles, vanishing as soon as we try to measure them. And still more linger in the very fabric of time itself, where past and future blur into something stranger than imagination. These are the questions that keep scientists awake at night. Questions that tear open the comfort of certainty. Questions that remind us that to seek the truth of the universe is to stand on the edge of the unknown, staring into a darkness far greater than ourselves. Since the dawn of awareness, the night sky has been humanity's oldest companion. To ancient stargazers, the heavens were a living canvas. The constellations rose and set with solemn precision, yet not all was steady. At times, new stars appeared where none had been before. Comets blazed across the sky like wandering spirits. Planets shifted, moving against the backdrop of distant suns. These irregularities whispered of something hidden, something beyond the reach of early understanding. Priests, poets, and philosophers wrote them into stories of gods and omens, not yet knowing that these same patterns would one day form the foundation of science. The mysteries began as questions carved into the silence of the night. Why do some stars wander while others remain fixed? Why does the moon swell and shrink in rhythm with the tides of the sea? Why do shadows lengthen differently as the year turns? These were puzzles, half seen, half understood. Yet each irregularity became a doorway to discovery. As time passed, humanity replaced myth with measurement. The ancient Greeks, through figures like Hipparchus and Ptolemy, began to record the shifting heavens with numbers. Centuries later, Johannes Kepler studied the erratic paths of Mars, finding not chaos but order hidden in ellipses. Galileo turned his telescope skyward and found mountains on the moon, moons circling Jupiter and stars beyond counting. With every new lens, the universe grew stranger, as though each attempt to bring it closer only revealed how much farther it extended. Centuries after those first glimmers, the tools of discovery changed again. The telescope became vast, its mirrors carved like the eyes of giants. The mountaintops of Earth bristled with observatories. Radio waves hummed from space, carrying signals from galaxies so far away their light had left before Earth even formed. Humanity learned to see not only with eyes, but with instruments tuned to every frequency of the cosmic spectrum. And in this modern age, the whispers of mystery became louder. Some arrived as paradoxes that unsettled even the greatest minds. Albert Einstein, when shaping the equations of general relativity, discovered that the mathematics did not predict a still universe. Space itself seemed restless, demanding either expansion or contraction. Yet the sky above appeared calm, the stars fixed. Troubled, Einstein introduced a strange term, a cosmological constant, meant to hold the universe in balance. He later called it his greatest mistake, though history would reveal otherwise. For in 1929, Edwin Hubble, observing faint galaxies through the 100-inch Hooker telescope, discovered the truth. The galaxies were not fixed. They were fleeing. The farther away they lay, the faster they retreated. The universe itself was expanding, space stretching like fabric pulled at every seam. The cosmological constant, once discarded, would return in another guise, reshaped by the discovery of dark energy. But at the time, Hubble's revelation transformed everything. The universe was not eternal and unchanging. It had a beginning. And with that realization came the first glimpse of the Big Bang. Yet even as the largest questions unfolded in the sky, the smallest mysteries emerged from the particle accelerators of Earth. In great underground chambers, beams of protons and electrons were flung into collisions at unimaginable speeds. In those fleeting sparks, unseen forces revealed themselves. Particles that could not be directly touched danced into existence for fractions of a second. Some obeyed the rules, others broke them. Neutrinos streamed through matter like ghosts. Quarks and gluons spun in an endless confinement, refusing isolation. Every answer fractured into deeper riddles. Einstein himself wrestled with this new world. He sought a unified theory, one elegant framework to bind gravity with the quantum fields. Yet nature resisted. The quantum world pulsed with uncertainty, probability woven into its very fabric. Particles existed in clouds of possibility until observed. The more precisely one measured their position, the less certain their momentum became. This principle of indeterminacy, uncovered by Werner Heisenberg, was not a flaw but a law, shattering the certainty of classical physics. Humanity had stumbled upon puzzles by daring to look too far, and again, by daring to look too close. The cosmos did not yield easily. Each discovery revealed not closure but depth. Ancient irregularities in the sky had led to the realization that Earth was not the center of all things. The faint drift of galaxies had unveiled the expansion of the universe. And the invisible tremors and atomic collisions revealed that matter itself was not solid, but a flickering sea of probabilities. As the 20th century unfolded, the mysteries deepened further. The cosmic microwave background, first detected by Arno Penzias and Robert Wilson in 1964, arrived as a hiss of static in their antenna. At first they thought it was noise, perhaps pigeon droppings interfering with the signal. But it was no accident. It was the afterglow of creation itself, the faint echo of the Big Bang stretched across the sky. That ancient light confirmed that the universe was not eternal. It had a fiery birth, a moment when time and space themselves emerged. Yet even this revelation carried questions it could not answer. Why was the early universe so smooth, nearly identical in every direction, when the laws of physics suggested it should have been far more chaotic? What force had driven its rapid inflation in the first fractions of a second? And what remains unseen in the 95% of the cosmos made not of stars or planets, but of dark matter and dark energy? The history of discovery is not a tale of certainty gained, but of certainty lost. Each revelation has peeled away the comfort of simplicity, leaving the cosmos larger, older, stranger than before. What once seemed eternal was revealed to have a beginning. What once seemed solid was revealed to be uncertain. And what once seemed knowable is now known to be far vaster than imagination itself. The universe is a puzzle that resists completion. Ancient eyes looked upward and found irregularities they could not name. Modern scientists built telescopes, satellites, and colliders to probe the heavens and the quantum realm, only to find anomalies that remain unresolved. From the cosmological constant to the accelerating universe, from the behavior of quarks to the whisper of neutrinos, every layer of discovery has shown us that mystery is not an obstacle to truth. Mystery is truth itself, unfolding one revelation at a time. And so humanity continues to stumble forward, caught between the infinite above and the infinitesimal below. With each step, the questions grow heavier. Each discovery is a reminder that to look too closely or too far is to risk unsettling the very foundations of understanding. Yet it is in this unsettling that science thrives. It is in the widening of mystery that wonder endures. The universe has never conformed to expectation. Each time science begins to believe it has carved order from the unknown, reality answers with defiance. It is in these moments when discovery collides with assumption that the true nature of shock emerges. Not the sudden jolt of fear, but the slow, inexorable realization that everything once trusted may no longer stand. For centuries, humanity believed that the stars and galaxies were enough, that the luminous matter visible to the eye and measurable by telescope accounted for the cosmos entire. But in the 20th century, the light itself betrayed that assumption. Vera Rubin, studying the rotation of galaxies in the 1970s, noticed something strange. The stars at the edges of spiral galaxies did not move as Newtonian gravity predicted. They should have lagged behind, drifting more slowly than their inner counterparts. Instead, they raced at near equal speeds as though bound by an invisible hand. This was not a quirk. It was consistent across galaxy after galaxy, across cluster after cluster. Something unseen was holding them together, outweighing the stars themselves. Rubin had revealed a cosmos where the visible was only the surface of a hidden ocean. Beneath it lay something immense, something without light, without radiation, yet exerting gravity across the universe. It was named dark matter, not for understanding but for absence. To this day, its true nature remains concealed. Is it a particle undiscovered? A relic of the Big Bang, a flaw in the laws of gravity themselves. No telescope has yet pierced its veil, and so it endures as one of the greatest shocks of modern science. That everything visible, every planet, star, and galaxy, makes up less than 5% of the universe. The rest remains unseen. If dark matter was a whisper of mystery, dark energy became a roar. For decades, cosmologists assumed that expansion, ignited by the Big Bang, would slow under the pull of gravity. The universe might collapse into a fiery end or coast forever toward stillness. Either path seemed possible. But in 1998, two independent teams observing distant supernovae found something that shattered both visions. The expansion was not slowing. It was accelerating. Space itself was stretching faster with time, galaxies fleeing more quickly the farther apart they drifted. This was no minor correction. It meant the dominant force of the cosmos was not gravity, not matter, not even the sum of known particles, but an unseen energy woven into the very fabric of space. Dark energy, as it was called, accounted for nearly 70% of existence, yet no one knew what it was or why it surged. Was it a property of the vacuum itself? A ghost of Einstein's cosmological constant revived from his discarded equations? Or was it something stranger, a force that could evolve and shift, perhaps even reverse? The discovery rewrote every model, forcing scientists to face a universe not only vaster than imagined, but driven by an unknown power they could not yet name. And while the largest scales of existence revealed their paradoxes, the smallest scales whispered their own. In the quantum realm, entanglement stood as both marvel and menace to reason. First noted by Einstein, Podolsky, and Rosen in 1935, it described particles linked in such a way that the state of one instantly defined the state of the other, no matter the distance between them. Einstein derided it as spooky action at a distance, for it seemed to violate the speed of light, the very limit he had set as the universe's ultimate law. Decades later, experiments proved that entanglement was real. Particles separated by kilometers, even by continents, behaved as though connected by invisible threads outside the reach of space and time. This was not communication, at least not in the classical sense. No signal traveled, no message passed. Yet the correlation was undeniable, beyond randomness, beyond coincidence. It suggested that the universe was not built from independent parts, but from relationships, an indivisible whole where distance is an illusion. To physicists, entanglement was not merely unsettling. It was a fracture line in reality itself. It suggested that locality, the idea that objects are only influenced by their immediate surroundings, might be an illusion. It suggested that information is deeper than matter, that the fabric of existence may not be built of particles or waves, but of correlations and patterns that transcend physical separation. Quantum mechanics had already forced a reckoning with uncertainty. Entanglement now forced a reckoning with connection. These shocks, dark matter, dark energy, entanglement, were not just discoveries. They were wounds to certainty. Each one cut away a layer of comfort, exposing deeper mysteries beneath. And with each, the emotional weight fell heavily upon the scientific mind. For scientists are not immune to wonder nor to doubt. They too are children of curiosity, staring into the dark with fragile tools of reason. When the universe resists their equations, when data contradicts expectation, the cost is more than intellectual. It is sleeplessness. It is the haunting awareness that the ground beneath thought is shifting. Imagine devoting decades to the belief that the universe is slowing down, only to find it racing apart under a force you cannot name. Imagine realizing that all of human history, every star ever seen, is a fraction of reality, with the rest cloaked in shadow. Imagine the discomfort of knowing that particles, once thought independent, exist in ways that defy the very notion of space and distance. And yet, this is where science thrives, not in comfort but in confrontation. The universe whispers truths, but they are truths without translation. Each paradox is a language not yet spoken. Each contradiction is a doorway to a deeper order, hidden beyond the reach of current thought. Dark matter holds galaxies in its unseen grip. Dark energy tears them apart with accelerating force. Quantum entanglement binds particles across the abyss of distance. These are not failures of science, but signs that the cosmos is vaster than comprehension allows. They are reminders that human knowledge is not a finished map, but a candle burning in an endless night. The shocks of discovery are not the end of understanding. They are its beginning, for in every paradox lies the seed of revelation. In every contradiction lies the possibility of a greater truth. And though scientists may lose sleep, though certainty may crumble, it is in this crumbling that progress is born. The universe is not obligated to be simple. It is not bound to obey intuition. It is what it is. Strange, immense, beautiful, and beyond expectation. To encounter its shocks is to be reminded that humanity's search is not for answers alone, but for the humility to accept that the greatest truths may still lie beyond the horizon of thought. Every age has built its own lanterns against the darkness. For the ancients, it was polished stone and primitive lenses, raised to the night in wonder. Today, the lanterns are machines of astonishing power, vast instruments that stretch human senses across the fabric of the cosmos. They do not simply magnify what is already seen. They create new sight, opening windows onto realities no human eye was built to perceive. And yet, the deeper these instruments peer, the more they reveal a truth that unsettles. Clarity does not end mystery. It deepens it. The Hubble Space Telescope, launched in 1990, became one of the greatest instruments of this age of revelation. Orbiting far above Earth's turbulent atmosphere, Hubble gazed into the depths of time with an unblinking eye. Its images of galaxies billions of light-years away reshaped human understanding of the universe. The Hubble Deep Field, a patch of sky no larger than a grain of sand held at arm's length, revealed thousands of galaxies hidden in what had seemed like empty darkness. Each one was an island of billions of stars, frozen at different stages of cosmic history. It was a vision so staggering that it forced cosmology into a new era, yet even Hubble had its limits. To glimpse the earliest galaxies, to peer into the faintest light born after the Big Bang, a new instrument was required. And so the James Webb Space Telescope was born, unfolding in 2021 like a golden origami of mirrors, carried to a place where Earth and Sun balanced its delicate position. With its infrared gaze, Webb became not only a telescope but a time machine, capable of seeing light stretched for over 13 billion years. The revelations came swiftly, and they shocked. Galaxies appeared too large, too structured, too early in cosmic history. According to standard models, such immense formations should have taken billions of years to emerge. Yet Webb's vision revealed them thriving just a few 100 million years after the Big Bang. The laws of structure formation, once thought settled, began to fracture under the weight of this evidence. Was the physics of the early universe misunderstood? Did dark matter clump more quickly than believed? Or had some unknown force accelerated the birth of stars and galaxies in those first moments? Each image from Webb, instead of offering answers, opened deeper questions, hinting at a cosmos far stranger than imagined. If telescopes look outward and backward in time, colliders like the Large Hadron Collider look inward, probing the smallest constituents of matter. Beneath the border of Switzerland and France, the LHC stretches in a ring 17 miles long, smashing protons together at energies never before achieved. Each collision is a recreation of conditions that existed microseconds after the Big Bang, a flash of primordial reality reborn under Earth's surface. The LHC confirmed triumphs of the Standard Model, most famously with the discovery of the Higgs boson in 2012, a particle that gives mass to matter itself. Yet as soon as the triumph came, so too did unease. For the Higgs was found, but nothing more. Physicists had expected doors to open onto supersymmetry, hidden dimensions, perhaps even clues to dark matter. Instead, the universe remained curiously silent. And yet subtle anomalies flicker at the edges of the data, muons decaying at unexpected rates, hints that certain particles may be interacting beyond the known forces. The Standard Model holds, but only by threads, suggesting it may be only a fragment of a deeper law not yet glimpsed. Beyond colliders, the search continues with detectors built not for sight but for silence. Deep underground, in chambers carved from ancient rock, instruments wait for the faintest interactions of neutrinos, particles so elusive that trillions pass through every human body each second without leaving a trace. Long thought to be massless, neutrinos revealed themselves to oscillate between types, a behavior only possible if they carry mass, however slight. This discovery shattered a cornerstone of particle physics and demanded revisions to the Standard Model. Yet their exact masses remain unknown, their role in cosmic evolution uncertain. Some theories suggest they shaped the early universe, tilting the balance between matter and antimatter, Others hint that they may carry connections to physics not yet imagined. Together, these instruments, Hubble, Webb, the LHC neutrino detectors, and countless others, form a network of senses stretching across scales of existence. They peer outward into the vastness of galaxies, inward into the quantum foam, and downward into the ghostly streams of invisible particles. The data pours in endlessly, a flood of numbers translated into images, spectra, collisions, and probabilities. And with every revelation, the pattern repeats. What is found opens more than it resolves. The galaxy's too massive, too early. The Higgs boson standing alone where companions were expected. The neutrino carrying mass in defiance of expectation. The universe answers questions not with conclusions but with paradoxes. This layered mystery carries an emotional weight, for it demands humility. Scientists trained to believe in progress through clarity now face a reality where clarity itself multiplies uncertainty. The James Webb Telescope does not simplify the birth of galaxies. It complicates it. The Large Hadron Collider does not complete the standard model. It fractures it. Neutrino experiments do not close questions. They open new ones. It is a reminder that science is not a path to certainty, but a confrontation with wonder. Each layer of investigation is peeled back, only to reveal another beneath. The deeper the instruments probe, the more fragile human assumptions appear. The universe does not bend to expectation. It resists. It conceals. It entices with whispers of truth hidden just beyond reach. And so humanity stands in a place both extraordinary and unsettling. Never before has so much data flowed from the cosmos. Never before has technology extended vision so far or so deep. Yet never before have the foundations of knowledge felt so incomplete. The instruments of clarity have revealed that the universe is not a puzzle moving toward resolution, but an endless labyrinth, each passage opening onto another. To search is to accept this truth, that mystery is not temporary. It is permanent, woven into the structure of reality. The James Webb Space Telescope, the Large Hadron Collider, the detectors of neutrinos, they are not final answers. They are questions given form, machines that translate the silence of the universe into a language still unknown. The cosmos continues to withhold its deepest meaning. Galaxies burn and fade, particles collide and vanish. Neutrinos stream in endless rivers, and still the horizon of understanding stretches away. Every answer is a doorway. Every doorway leads to another room of shadows. And in the quiet between data points, in the silence of instruments waiting for the next signal, the universe whispers truths science cannot yet translate. The deeper science peers into the fabric of the universe, the more fragile that fabric begins to appear. What once seemed unshakable now trembles under the weight of discovery. Space, time, and matter no longer stand as immutable truths. They dissolve into riddles that stretch human reason to its breaking point. The universe reveals not only its vastness but its instability. Mystery deepens, and with it grows the haunting suspicion that reality itself may be less solid than once believed. For centuries, the Big Bang has been the great anchor of cosmology, the singular beginning, the moment when time and space erupted from nothing into everything. The discovery of cosmic expansion and the faint glow of the microwave background seemed to confirm it. The universe, once thought eternal and unchanging, had a birth. But what if the story is incomplete? What if the Big Bang is not the beginning, but merely a chapter in a larger narrative that human minds can scarcely imagine? Some theories suggest that our universe may have emerged from a prior one, born from the collapse of an earlier cosmos that contracted into a dense singularity before exploding outward again. Others imagine a multiverse where countless universes bud and expand like bubbles in a cosmic sea, each with its own laws of physics, its own birth and death. The Big Bang in this vision is not creation but transition, a moment in a cycle without true beginning, without final end. If so, then the question of origin slips further from reach, replaced by the unsettling thought that beginnings themselves may be illusions. Yet the mystery runs deeper still. Within the very equations that govern quantum fields lurks the possibility of instability. The vacuum of space, far from empty, seethes with energy. Virtual particles flicker in and out of existence. Fields hum with latent potential. And hidden within this quantum sea lies a threat so profound it unsettles even the most rational minds. If the vacuum is not perfectly stable, then a bubble of lower energy reality could one day appear, expanding outward at the speed of light, rewriting the laws of physics as it spreads. This is the specter of vacuum decay. In such an event, atoms would dissolve, stars would extinguish, chemistry would collapse. Reality itself would be erased, replaced by a new and alien order of existence. Though the probability may be infinitesimal, the possibility cannot be dismissed. Calculations based on the Higgs boson suggest that our universe teeters on the edge of such instability, balanced precariously between stability and decay. If so, then the ground beneath all being is not as firm as it appears, but instead fragile, provisional, contingent on the hidden symmetries of fields we barely comprehend. And then there are black holes, the most enigmatic of all cosmic objects, whose very existence stretches human reason into paradox. Born from the collapse of massive stars, they are regions where gravity overwhelms every other force, crushing matter and bending space into wells from which even light cannot escape. For decades, black holes were thought to be eternal vaults, swallowing all information into an abyss with no return. Yet this idea collides with a law as fundamental as gravity itself, the law of conservation of information. In quantum theory, information cannot be destroyed. It may transform, scatter, or entangle, but it cannot vanish. Here lies the black hole information paradox. If black holes erase the information of everything they consume, then quantum theory breaks. If quantum theory holds, then black holes cannot be the silent erasers they appear to be. Stephen Hawking added further tension by showing that black holes are not eternal, but radiate energy, Hawking radiation, slowly evaporating over unimaginable timescales. But if they vanish completely, where does the information go? Is it smeared across the event horizon, preserved in faint ripples of quantum entanglement? Is it encoded in the radiation itself? Or does it escape through pathways unknown, hinting at new physics beyond imagination? Each possibility is profound. If information is preserved, then black holes become cosmic libraries, encoding the history of everything they consume in ways still unknown. If information is lost, then the foundations of quantum theory fracture, demanding a revolution in physics as great as any before. Either way, reality itself stands on trial, forced to reveal whether memory is eternal or fleeting. The emotional weight of these revelations is immense. For scientists, they are not abstractions but sleepless nights. The thought that the universe may be unstable, that existence itself rests on a precarious balance, is more than theory. It is existential. The suspicion that beginnings may be illusions unsettles the human longing for origin stories. The possibility that black holes might erase the record of reality strikes at the heart of meaning. For what is history, what is memory, if it can be annihilated by the cosmos? The closer humanity looks, the less solid reality becomes. Matter dissolves into probability, space into fields of energy, time into cycles without clear beginning or end, the very vacuum into the threat of collapse. Each layer once thought stable now reveals its fragility, its dependence on deeper structures not yet understood. The ground beneath existence seems to quiver, as though the universe itself were a question still being asked. And yet, within this escalation of mystery lies a strange beauty. For the deeper the paradox, the greater the invitation to wonder. These are not failures of science. They are the frontier, the place where human imagination strains to meet reality. The Big Bang, vacuum decay, the black hole paradox, each is a reminder that the universe is not bound to satisfy human expectation. It is free to be strange, to be vast, to be greater than thought allows. To live in such a universe is to live without certainty, but not without meaning. For it is in the confrontation with mystery that humanity discovers its true place, not as masters of the cosmos, but as witnesses to its unfolding. The questions may never be fully answered. The origins may never be fully known, but the act of seeking, of turning instruments toward the silence and asking what lies beyond, is itself a kind of participation in the great story of existence. The mysteries have become existential. The universe does not merely resist explanation, it resists assurance, it resists permanence, it resists the comfort of solid ground, and so humanity continues staring into the abyss, listening to the whispers of a reality that may never be fully translated. The farther science reaches into the unknown, the more it finds itself standing at the edge of speculation. The great instruments of modern discovery, telescopes, colliders, detectors, deliver torrents of data. Yet when the data collides with paradox, Mathematics and imagination must extend where observation cannot yet follow. Here, in this fragile territory, science touches its most daring form. It is no longer only measurement. It is vision. Among the most pressing mysteries lies the question of dark energy. Since its discovery in 1998, it has remained the dominant force in the universe, accelerating cosmic expansion with a strength that accounts for nearly 70% of all existence. And yet its identity is a void in knowledge. Some physicists interpret it as the cosmological constant, a term once discarded by Einstein, then revived as the simplest explanation. In this view, dark energy is a property of the vacuum itself, a pressure woven into space that stretches it outward eternally. But the cosmological constant brings with it a puzzle. When physicists calculate the energy of the vacuum using quantum field theory, the result is catastrophically larger, by factors of trillions, than the value observed. It is a mismatch so extreme that it suggests something profound is missing from human understanding. To resolve this, others propose quintessence, a dynamic field that evolves with time, altering the strength of dark energy across cosmic history. Unlike the static cosmological constant, quintessence could wax and wane, perhaps even reversing to pull the universe back into contraction. If true, it would mean that cosmic destiny is not fixed but alive with change, guided by a field still invisible to every instrument. Beyond dark energy lies an even more audacious speculation, the multiverse. The standard Big Bang suggests a beginning, but inflation theory, developed to explain the uniformity of the early cosmos, opens the door to something vaster. Inflation describes a moment when space itself expanded faster than light, smoothing the young universe into its present form. But some versions of inflation do not end everywhere at once. Instead, they continue eternally, spawning pocket universes within an infinite cosmic sea. Each bubble expands with its own laws of physics, its own constants, perhaps even its own dimensions. In this vision, our universe is not unique but one of countless others, a single droplet in an endless foam of realities. The multiverse is controversial, for it lies at the edge of science. By definition, other universes cannot be observed directly, yet its mathematics arises naturally from inflation and from the equations of string theory. Some scientists resist it as untestable, while others accept it as the most elegant explanation of why the constants of our universe seem so improbably suited for life. If there are countless universes, each with different laws, then ours is simply one where the conditions happen to align. To some, this weakens the uniqueness of existence. To others, it expands wonder to the infinite. At the heart of all these mysteries lies the fracture between the two greatest theories of modern physics. Einstein's general relativity describes gravity as the curvature of spacetime, shaping the motions of planets, stars, and galaxies with astonishing precision. Quantum mechanics, by contrast, rules the microscopic realm, where uncertainty and probability govern the dance of particles. Each theory is successful within its domain, yet they remain irreconcilable with each other. At the extremes, inside black holes at the instant of the Big Bang, the two collide in contradiction. The search for quantum gravity is the search to heal this divide. String theory offers one path. It proposes that the fundamental building blocks of reality are not particles but tiny vibrating strings, their modes of vibration giving rise to quarks, electrons, and forces. String theory requires extra dimensions beyond the familiar four, hidden from view, curled into scales too small to detect. Its mathematics is breathtaking, unifying all forces in principle, but its predictions remain beyond current experiments. Loop quantum gravity takes another path, discarding strings in favor of a universe where space itself is quantized, woven from finite loops that form a cosmic fabric. In this vision, spacetime is not smooth but granular, like a tapestry stitched from indivisible threads. Loop quantum gravity suggests that singularities may not exist, that the universe may bounce rather than break, transforming black holes in the Big Bang into passages, not ends. Both theories remain incomplete. Both carry beauty and burden. Neither has yet delivered the decisive evidence to lift it from speculation to law. But in their daring, they reveal the human drive to imagine what lies beyond measure. At the boundary where relativity and quantum mechanics resist reconciliation, scientists continue to propose ideas that blur the line between mathematics and imagination. The holographic principle suggests that reality itself may be two-dimensional, with the three-dimensional world emerging as a projection, like a cosmic hologram. In this view, the information of everything within a volume of space is encoded on its boundary, a radical rethinking of existence inspired by the paradoxes of black holes. Other theories suggest time itself may not be fundamental, but emergent, a property that arises from deeper processes yet unknown. If so, then the flow of past to future is not the foundation of reality, but a phenomenon like temperature or pressure, dependent on the collective behavior of hidden constituents. Such a possibility reshapes not only physics but philosophy, challenging the very experience of being. These ideas live at the speculative edge, where science walks hand in hand with wonder. They are not certainties but attempts to translate paradox into possibility. To propose a multiverse is to admit that what is seen may be only a fragment. To imagine quintessence is to accept that cosmic destiny is not fixed. To weave relativity with quantum mechanics is to confront the possibility that reality is stranger than either alone suggests. Speculation is not weakness. It is the frontier. From Copernicus to Einstein, every revolution began as a theory that defied the consensus of its age. Today, dark energy, the multiverse, quantum gravity, and the holographic principle stand as such frontiers. Each is fragile, incomplete, but each is a torch carried into the shadows where data has not yet reached. The speculative edge is where science becomes most human. It is where imagination stretches against the silence of the unknown, where mathematics becomes a language not only of logic, but of vision. These frameworks may fail, they may fracture under future evidence, or they may in time reveal truths that reshape existence itself. Until then, they remain as bridges across the abyss, fragile, uncertain, luminous with possibility. The universe has given humanity glimpses of its vast machinery, yet the deepest workings remain hidden. Between dark energy's enigma, the multiverse's audacity, and the fracture between relativity and quantum mechanics, lies the greatest mystery of all, that reality itself may still be beyond the horizon of thought. The pursuit of knowledge has always required tools. In the beginning, those tools were little more than sharpened stones held against the sky, the eyes of early astronomers straining toward the patterns of stars. Today they are vast machines, cities of steel and glass, networks of mirrors, and detectors buried deep within mountains. These instruments are not merely tools. They are extensions of human curiosity, built to translate the silence of the universe into language. At the forefront of this new age of discovery stands the James Webb Space Telescope. Orbiting 1,000,000 miles from Earth at the Lagrange point, Webb's golden mirrors open like the petals of a cosmic flower, tuned to the faint glow of the infrared spectrum. Unlike its predecessor, Webb peers into the first billion years after the Big Bang, detecting galaxies whose light has traveled for over 13 billion years. In those ancient signals lie the answers to questions of structure and origin. Already Webb has revealed galaxies too massive, too luminous, too mature for their place in time. Its data challenges models of cosmic evolution, whispering of forces still unmeasured, of physics not yet written. But Webb is not alone. Soon it will be joined by Euclid, a European mission launched to map the dark geometry of the cosmos. Euclid's purpose is audacious: to chart the distribution of dark matter and measure the influence of dark energy across billions of galaxies. By tracing how structures form and stretch under unseen forces, Euclid seeks to unravel why the universe accelerates in its expansion. Together, Webb and Euclid form twin eyes, one gazing into the deep past, the other scanning the scaffolding of the present universe. On Earth, another eye prepares to open. The Vera C. Rubin Observatory, rising in the Chilean Andes, carries a mirror over 8 meters wide and a camera the size of a small car. Its mission is to conduct the legacy survey of space and time, capturing the entire southern sky every few nights for a decade. It will generate a cinematic record of the universe in motion. Supernovae erupting, asteroids drifting, galaxies colliding. More than a snapshot, it will be a chronicle, revealing how cosmic structures shift, how dark matter pulls at the edges of galaxies, how dark energy stretches the void. Rubin will not only map the heavens, it will watch them live. If telescopes open the sky to vision, other instruments open it to sound. In 2015, LIGO, The Laser Interferometer Gravitational Wave Observatory recorded the faint ripple of space-time as two black holes merged over 1 billion light-years away. The signal lasted only fractions of a second, but it confirmed a prediction of Einstein made a century earlier. For the first time, humanity had not only seen the universe but heard it. Gravitational waves are vibrations of space-time itself, carrying messages from cataclysmic events invisible to ordinary light. Since that first detection, LIGO, joined by Virgo in Italy and Kagra in Japan, has recorded dozens of such events: collisions of black holes, mergers of neutron stars, cosmic dances that shake the fabric of reality. Each detection is not only confirmation but revelation. Gravitational waves carry information about the most extreme conditions in the cosmos, where matter is crushed to densities beyond comprehension, and gravity bends time into knots. They offer glimpses into physics at its limits, into realms no laboratory can reproduce. With each vibration, space-time itself becomes an instrument, singing its ancient songs into detectors built with precision beyond imagination. While telescopes and observatories look outward, particle colliders look inward. The Large Hadron Collider continues to probe matter at its smallest scales, recreating the furnace of the early universe. Plans already stretch toward future colliders, machines even larger, spanning entire nations, designed to reach energies beyond the LHC. These colossal rings of superconducting magnets are not built for spectacle. They are built to ask questions too deep for smaller experiments to touch. Are there hidden dimensions beyond the familiar 3 of space and 1 of time? Are there undiscovered particles that form the dark matter binding galaxies? Is the Higgs boson truly alone, or is it part of a larger family of fields and forces still unseen? Beneath mountains and deep within ice sheets, detectors listen for neutrinos, the ghost particles that rarely touch matter. In Antarctica, the Ice Cube experiment uses a cubic kilometer of transparent ice as its medium, watching for flashes of blue light when neutrinos collide with atoms. These rare collisions reveal neutrinos born in the hearts of exploding stars, in the accretion disks of black holes, perhaps even in events that trace back to the first moments of creation. In Japan, Super Kamiokande watches for neutrinos passing through its vast chamber of water, a silent witness to the unseen currents of the universe. These experiments extend perception into realms once thought inaccessible, building a new language from the faintest of signals. The scale of these machines reflects the scale of the questions they confront. Humanity has built telescopes the size of tennis courts and detectors the size of skyscrapers. It has constructed laboratories beneath mountains and observatories in deserts, in space, and under ice. Each instrument is an act of faith and curiosity. Each is a cathedral built not to gods but to the possibility of understanding. Yet the paradox remains. With each revelation, the mystery deepens. Webb shows galaxies too mature for their age. Euclid prepares to reveal a map whose structures may not align with predictions. Rubin will watch the universe change before our eyes, but it may expose irregularities beyond theory's grasp. LIGO hears the songs of space-time, but each note raises new questions about matter, energy, and the fate of stars. Colliders break matter apart, but the pieces do not yet reveal the whole. Neutrinos stream endlessly, yet their nature remains incomplete. The relentless search continues. Humanity builds machines the size of cities, detectors larger than mountains, telescopes that float in the silence beyond Earth, all to chase whispers from the void. The effort itself is a kind of poetry, a species born on a fragile planet daring to reach into the abyss, crafting instruments capable of listening to the heartbeat of the cosmos. Science, at its heart, is not a path toward closure but an unending dialogue. Each machine is a voice in that dialogue, each experiment a question posed to the universe, and the universe, vast and patient, answers not with certainty but with echoes. Those echoes carry both revelation and riddle, both beauty and paradox. The story of these instruments is not just technical, it is human. Each telescope, each collider, each detector is built from the collective imagination of thousands. They are embodiments of patience, of faith and reason, of the belief that silence can be translated if only one listens long enough. They are reminders that knowledge is not given freely, but earned through generations of effort, through ingenuity and persistence. In their relentless search, these machines become more than steel and glass. They are the bridges between the finite and the infinite. They are the instruments of clarity that reveal the depth of mystery. They are humanity's answer to the void. What does it mean that reality itself resists understanding? For centuries, science has been carried forward by the belief that the universe can be known, that beneath the complexity of stars and atoms lies an order waiting to be revealed. Yet at the summit of modern knowledge, the horizon remains shrouded. Each answer dissolves into paradox. Each discovery opens onto a deeper mystery. The closer the search comes to truth, the more elusive truth becomes. This is not failure. It is revelation. The universe does not hand over its secrets as a final, completed map. Instead, it reveals itself as layered, infinite, unfinished. A book whose pages multiply as they are turned. A song whose final note is never played. The resistance of reality is not a barrier, but a mirror of human longing. For what is curiosity if not the recognition that the unknown will always remain? Humanity's restless spirit has carried it from caves lit by fire to telescopes orbiting the void. The same curiosity that once studied sparks leaping from wood now studies firestorms in galaxies, explosions of stars, and the rippling of space-time. The same instinct that carved stones into tools now builds machines that span nations, colliders that recreate the first seconds of creation. The continuity is unbroken. The questions have grown vaster, but the hunger is the same. To stare into the mysteries of dark matter, dark energy, and black holes is to stand on the edge of meaning itself. The recognition that the universe is stranger than imagination is not despair, but wonder. It means that existence is not a closed box, but an open horizon. That human beings are not at the end of knowledge, but at the beginning of something greater than knowledge. Even the paradoxes, the contradictions that erode certainty, are luminous. They show that the laws once thought final are provisional, that the universe is free to be different from expectation, free to astonish. The Big Bang may not be the beginning. Black holes may not erase memory. Vacuum may not be stable. These are not failures of theory. They are triumphs of discovery. For to find that reality defies imagination is to prove that imagination has not yet reached its limit. Science has never been about certainty. It has always been about awe. Copernicus displaced Earth from the center. Darwin revealed life's tangled history. Einstein bent time and space. Each revelation unsettled, yet each expanded the horizon of wonder. The same is true now. To know that 95% of the universe is unseen is not ignorance. It is the recognition that the cosmos is deeper, richer, more abundant than sight allows. There is poetry in this unfinishedness. The stars themselves are unfinished, born from clouds, burning for eons, dying into dust that seeds new stars. Galaxies are unfinished, colliding and merging, reshaping the heavens across billions of years. Even the universe is unfinished, expanding, evolving, perhaps birthing new worlds beyond the horizon. And humanity too is unfinished, shaped by the questions it dares to ask, by the mysteries it dares to confront. Scientists lie awake at night not in fear, but in awe. They wrestle not with despair, but with the immensity of the unknown. The insomnia of curiosity is not a torment. It is a privilege, the recognition of living in a universe vast enough to resist comprehension. To struggle against paradox is to touch the boundary of truth. To gaze into mystery is to become part of the story of mystery itself. In the end, these great riddles, the unseen matter, the accelerating void, the entangled particles, the paradox of black holes are not failures of science. They are its most luminous triumphs, proof that the universe is not simple, not small, not limited to human expectation, proof that reality is more than imagination has yet dreamed. And so the search continues. The telescopes will look farther, the colliders will reach deeper, the detectors will listen longer. Each will uncover not an end but another beginning. The universe is unfinished. It waits for humanity to keep asking, to keep building, to keep wondering. To live in such a universe is to live not with certainty, but with awe. Not with final answers, but with the endless unfolding of questions. This is the gift of science, not the illusion of completeness, but the truth of mystery, not the comfort of resolution, but the beauty of pursuit. The story does not close. It opens. The last word is not an answer, but an invitation.